Brian's agreed to lead off this fall edition of SMACCM, and he's going to talk about emulating, and preserving our digital heritage. So I'm going to stop talking right now and turn it over to the other Brian in the department, and take it away.
All right, thank you. Well, it is a packed house in here. I assume most of you are getting the extra credit I extended my students. If not, I'd give you 150 extra credit for what it's worth. Today's talk is sort of a departure, I suppose, from some of the SMACCM topics. We're going to be talking about a topic that's usually reserved for sort of a computer engineering, computer science background, but hopefully in a way that appeals to you, appeals to maybe the same math center of your brain that everything else appeals to, and hopefully is of interest to you. So, in talking about emulation, and especially with the tagline, preserving our digital heritage, I want to begin with a couple of examples and ask you a question. That question is this: can you imagine what it would be like if to watch the movie The Wizard of Oz, you had to purchase and operate a magic lantern from 1939? Like, that would be silly. I don't think I would have ever watched it. To be honest, I don't think a lot of people would have watched it. What if, in order to play Dark Side of the Moon, you had to buy a reel-to-reel Studio Mastery recorder? Not to say anything of the peanut butter and chocolate experience that is combining the two of them. But still, we love these things and know these things because of the way that they've been handed down from generation to generation. Many of you, especially my students, were born well after Dark Side of the Moon came out, and even longer after Wizard of Oz came out, and yet these things are still the cultural touchstones that we're all familiar with. The reason for that is we are all cultural archivists, whether we understand it or not. We are our own anthropology department. Your houses no doubt contain many CDs and MP3 players, so you have music that was recorded well before you were born and well before these devices were manufactured. You have films in which people have acted, played their part. Some of them have passed away since. You have books that were written hundreds of years ago, maybe thousands. And your home is stocked with the results of all the cultural fads that have played out in the 80s, 90s, and 2000s since. We are all cultural archivists, whether we understand it or not. And the transmission of these things comes down to us through a variety of media, through a variety of manufacturing processes, which are sort of still ongoing in our day. Now, this poses a problem as far as a computer scientist is concerned, because if I have a Rubik's Cube, I have that same Rubik's Cube, that same hunk of plastic, and I can pass that down to my kids, and provided they don't step on it or sit on it, they can pass it down to their grandkids. I can do the same thing with a book. I can maybe even do the same thing with a music player, but I can't necessarily do that with a piece of software. Because the general rule in technology is that new tech displaces the old. How many of you still have your first iPod at this point? If you do, shame on you. You should be recycling this. What is wrong with you? Where do you get new hardware when it's out of print? You can go to eBay, but eventually that well's going to dry up. Sounds very Asimov, last question, what we're talking about. And that leaves out the question entirely of what are we going to do with the software for these old machines? Many of the historical artifacts of the computer age would have been lost in space and time if it weren't for things completely outside the control of the people who designed those programs. I've got a quote here from Ben Edwards, who's a columnist for Technologizer, writing on the subject, Why History Needs Piracy. Not that I'm advocating piracy. He wrote, if copy protection schemes had been foolproof and copyright law had been obeyed, most of these programs would now be gone forever. You see, for decades, games and other forms of software that were put out sort of mass-produced and mass-consumed by people with computers had various schemes to prevent people from either making copies or even running them without the explicit permission of the original developers. Some of whom are now living up in the mountains, I'm sure. I know at least one who's bought a refuge out in Hawaii. I don't know him personally, I know of him, okay? But these men and women designed their software not only to run only for authorized users, but they came up with increasingly sophisticated ways to make sure that that software, their precious cargo, would never ever come off the floppy disk no matter how hard you tried. They would do things like purposely breaking the schemes that people were using. They would inject bad sectors into their data at crucial places so that their software would run, but if Windows or some other operating system tried to copy it, it would come out as an invalid file. Lots of tricks like that that were designed to keep their software, which they intended to use sort of as their livelihood, from ever coming off of the plastic and magnetic tape inventions that had carried them. So, if this is the case, and if these games and programs that people had designed in the 80s and 90s were so designed as to never come off of those, what are we going to do when the devices and the media slowly but surely begin to corrode? Those of you who've been thinking about copying the box of floppies your parents gave you and that's been sitting in your closet for a while, it's probably already too late for you guys. Those magnetic charges have dispersed a long, long time ago. Those of you who got on the first generation of the CD reading and writing drives, it's probably running out for you too. The first generation of CDRs oxidized on average about 5 to 10 years ago. So, if we were never intended to copy these things, I guess what that boils down to is we're going to have to buy the White Album again, right? We, as a culture, have invented increasingly disposable things to amuse ourselves with. Enter the emulator. The emulator was first introduced to me as a freshman in high school as a way to play old video games, but doesn't have significance beyond that. Before we get any further, if you've never heard of an emulator is a program that perfectly imitates the behavior of either a software or a hardware system that came before it in a new context, in a new way. And we're probably already familiar with this to one extent or another. After all, we run much newer computers here than probably you had at home. If you ever ran a computer with Windows 98 or Windows 95 on it, you're running an emulator now, whether you realize it or not, because that old software and those old files don't work on new things. You can't run a 16-bit program on a 64-bit processor without some level of emulation. And whatever nostalgia is associated with 80s culture and with the video games that came out of that, without some level of indirection away from the original hardware, the shrinking pool of devices that were manufactured in that day is drying up, and those things will eventually disappear to be dramatic, into eternity. So I want to back up for a minute and talk about 3 men that made an impact on my development as a computer scientist. You see, the project that we're going to be talking over today, the project is one that I began when I was an undergrad as a hobby project. And it was because of knowing about these 3 that the project sort of came to fruition. Some of you may have seen these photos before. The man on the left is Alan Turing, and the man on the right is John von Neumann. These 2 were both very, very influential thinkers in their day. They both lived and died around 1900 to 1950. Man on the left here is Alan Turing. Alan Turing was a mathematician, but to say that sort of sells him short. The man was brilliant and prolific. He was a mathematician during World War II. He was a cryptanalyst. He helped break Nazi codes. He's called the father of computer science for a number of reasons. He and his advisor, Alonzo Church, were both very interested in the question, can everything be answered mathematically? In other words, if you pose a question in the form of a mathematical equation or theorem, can you prove it, yes or no? And if so, is there some completely unambiguous, completely mechanical way of doing it? Now, before they came along, a man named Kurt Gödel proved that there are a class of problems you can solve and a class you can't. So upon hearing about this, both Church and Turing, sort of independently at the time, began working on a way to build what would become a universal computing machine. And Turing was the first one to sort of formalize it. See, Turing was clever. He realized that as a thought experiment, if he built a machine that was capable of a certain set of things, any other machine that simulated his sort of theoretical machine would have the same power as it did. This diagram up here is a Turing machine. Some of you may have heard that term. I know my 150 students have. A Turing machine was a very, very simple computer. It had only a handful of parts, really. You didn't necessarily have to build one of these, although some people have in more modern times. A Turing machine was a spool of tape with a list of characters on them, symbols. It could be numbers or letters, or anything really, as long as the tape head, which was a mechanism that could move along the tape, could read those symbols and write more down. So to program a Turing machine, you didn't write in a programming language like Python or even assembly or machine language. To write a program in a Turing machine, you would come up with a series of rules. If the machine was in a certain state and it read a certain letter, you'd write another letter in its place and move either left or right on the tape. That's it. That's all there was to it. There were no complicated copy protection schemes for sure. There were no other pieces of architecture really involved. And so his sort of abstract computer model, made up of a series of these states and transitions, formed the basis for his idea of computability theory. And by proving that not only could you simulate other computers with this, but other computers could simulate Turing's machine, he and Church, sort of, again, independently, formed what's now known as the Church-Turing thesis, which I have up here in a couple of different ways. Given enough time and space, one of these guys with a tape head, moving, reading a letter, writing a letter, can do anything any computer in the universe can do. In other words, they all have the same ability to solve problems. Whether you have an NSA-style complex of supercomputers and code-breaking machines, or whether you have an Android phone, given enough time and enough space, you can do the same things with them. Hold on to that thought for a little bit. This man is John von Neumann. Now, von Neumann was not like Turing in that he wasn't necessarily as interested in computability theory, but von Neumann was an incredibly prolific mathematician, logician, mathematician, mathemagician. He did everything. He made contributions to ergodic theory. He made contributions to explosives theory. He was all over the place as far as his studies of concern were related to him. You could say he was a jack of all trades and master of all of them, but the way that John von Neumann came into my life was via a paper called First Draft of a Report on the EDVAC, which many undergraduate computer scientist students are forced against their will to read. In it, he talks about sort of a general purpose computer that he wanted to actually build and make practical. his architecture laid the groundwork for what is now called the stored program computer. And it looks sort of like this. In von Neumann's model, you have a bunch of devices connected electronically. You've got input devices that take some sort of user interaction into the machine. You've got output devices which take that data and interact back with the user. You've got memory in which you store a series of instructions, literally, in numbers. And you have a central processing unit, and that's the part where a lot of you go, I know CPU, right? Like an Intel. Not exactly. His model of a CPU was a little bit more abstract than that. You've got to remember, he was working in the days of vacuum tubes. But it was crucially divided into two things. A control unit, which was in charge of deciding where the program would go next, and an ALU, which was capable of doing mathematical expressions. So modern computers have all of these things built into them, right? We can look at a computer and say, it's a mouse, it takes user interaction, must be an input device. It's got a monitor on it, that displays information to a user, that's an output device. Maybe your headset's both. We know where the CPU's at, because when it goes wrong and we have to replace it, we know what we have to buy, etc. So John von Neumann and Alan Turing both made contributions that are around today. That's the first two men. The third man that I want to talk about is a fictional character named Joe Musashi. He was not a mathematician. He did not design a theoretical computer. He is not the father of computer science. He is a deadly, deadly ninja assassin. Joe Musashi was the protagonist of a video game called Shinobi that I got when I was in 4th grade. This was sort of the spark that set off the fire, and eventually here I am in a university CS hall talking about von Neumann and Alan Turing. When I was in 4th grade, my parents bought me my first video game, and it was off to the races. But as time went by, that cheaply produced handheld, eventually, stuff breaks on it, the monitor gives out, so you got to play it in the really bright sunlight, and batteries can't hold a charge anymore, and you simply can't do with it anymore. And so, for a time, it had been relegated to nostalgia for me. I thought back fondly upon those days, especially in the long days and nights of working on dissertations, and it brought me a level of warmth. At this point, all three of these came together for me, sitting in the back of a database class in my undergraduate education. By the way, I don't recommend that anybody just start an emulator in the back of a class because you're bored, but it is better than sleeping. BlameGear is my project that brings the three of these men together. It is a Game Gear emulator. It is a program that, given files representing the contents of the cartridges, again, the little plastic cartridges, you plug it back to the game, and you play like this. Given those dumps, I can play those games again. Let me explain how it works. This is the original hardware that we're talking about here. This thing is about as big as the projector. Really, you've got to get your hands around it like this to be able to play it. Inside, it has a CPU, an output device, input devices, and memory. So right off the bat, now we're beginning to connect the dots. How did von Neumann and Joe Musashi have anything in common? This looks a lot like a von Neumann architecture, doesn't it? And in fact, it is a von Neumann architecture. It's hard to find a computer in our day and age that isn't a von Neumann machine one way or another. So from the 50s, he's laughing at us for choosing an iPod over an Android device, because to him, they're all the same. Each one of these components communicates with each other with wires and signals and memory. And each one of these things has become a module of the program that we're talking about. So, to emulate the hardware, what I have to do is create programming code that mimics the behavior of the original hardware. If the hardware has a chip, I have a program that does the same thing that chip does. You give it the same input, it produces the same output. That's an emulator. If I have a register, which is a small little number that you can store inside the CPU or inside one of the devices, that's a variable now. Any of the mathematical functions that the ALU did with a bunch of logic gates and electrical signals, I can do inside my program. That's pretty easy. Even my 150 guys know how to write most of the stuff that my processor does. And anything that was sort of a complicated looking memory chips, appropriately dumped, can become a file on my computer or an array in my hardware or my RAM. So what we're talking about here is, as a programmer, an act of almost alchemy. I'm taking a piece of electrical hardware and I'm transmuting it, I'm mixing it together and making it into something that's mathematical. It's abstract. It won't ever rot. The buttons won't ever break. Right? The screen will never give out because I can always put it on another computer. It'll never oxidize in somebody's basement. The magnetism will never wear out. So, hobbyists like myself create the hardware that dumps the cartridge memory out to files on a computer. And they questionably legally distribute these. Homebrew developers, on the other hand, can use emulators like mine to create all new software. And indeed they do. Some people have emulators in their car running games that they made just because they have a sort of a labor of love involved in dealing with these things. Now, this is a diagram that sort of represents what we were up against. This is the diagram of all the little registers and memories and blocks inside a CPU. Looks pretty complicated, but if we count these things up, let's see, we've got 8 over here, maybe another 8 counting these guys. We've probably got less than 30 or 40 variables. 30 or 40 bytes. These were really old systems, so they didn't use a whole lot of memory. So if I can replicate the behavior of something in this diagram here, then I wonder what happens when I apply the original program I've dumped out to a file on my hard drive. Now, to be able to simulate the behavior of a CPU, I've got to know how a CPU works. So one of the first things that I found myself doing in building the emulator was sort of making a concerted effort to find all of the documentation I could possibly get on any of the hardware. And I found out actually, like WikiLeaks, a lot of the manuals and things for the hardware has been classified and reproduced and put out on the internet, so that wasn't too hard. But all CPUs have this in common. If you were to look inside a processor, you'd find the fetch, decode, execute. Because basically what we're talking about is a big number. Any program, and this is my dogma, right? This is my computing dogma. Anything inside a computer is binary, which means that a program is binary. And if it's binary, that makes it a number. Whether it's just 1, 0, or 1, 1, or whether it's a string of millions and millions of these bits put together, it's still a number. So what a CPU does is it looks down that number, it finds its spot, it pulls out a number, that's fetch. It looks up that number in a great big table and sees how to react to that number, given the state of the machine. And then it does it, that's execute. Now if that sounds familiar, right, if you're connecting the dots between the things I'm saying right now and the things I said 10 minutes ago, you'll say, wait a minute, where am I? Oh, right, that's a Turing machine. It is. Which means that it's as powerful and it fits neatly inside the same category of problems you could solve with any computer. Meaning, I've got a computer I can simulate on another computer. And that's exactly what I do, but instead of reading symbols that are just, squiggles or whatever off a tape, I'm reading a 0 to 255 number that I can go and I can look up in a table that has exactly 256 entries and I can see what to do with it. So as it turns out, Turing's machine is also still in use, one way or another. Granted, the tape isn't paper anymore. Now, it becomes a little bit more complicated to talk about how an emulator works when you talk about how do you connect the different pieces? How do we get the dots to come together? You say, Brian, I understand CPUs now, but how are you going to actually use the state of the CPU for anything? What difference? You said it's all binary, so how are we going to actually make this into an experience that you can share? Because absolutely, you care about experience. And I say, there are a couple of different ways that we can model this. Now, internally, a machine uses one of two mechanisms to talk to the different devices on it. It uses memory mapping, which again is just changing a number somewhere inside my memory. Or it uses port mapping, which is almost like a rudimentary, it's like email between the devices, where I'm sending bits of information, and then the device that receives it decodes it and executes it. So what ends up happening is we get behaviors arising out of the programs we're executing. Now, if every operation that my CPU does used to have very specific consequences, that means that I better have very specific consequences with what I'm dealing with now. It's possible for me to simulate, and this is kind of a dumb example, I'll preface it with that. It's possible for me to simulate a roller coaster and people riding on a roller coaster, going around the loop-de-loop, going over, down the hills, into the troughs, pulling off at the station, without emulating or simulating the movement of their hair on their heads. But I don't get that freedom with an emulator because it has to have exactly the same behavior as the original hardware. Every operation had very specific consequences, and the expert programmers who built their software on these platforms knew what those consequences were and depended on exactly the expected behavior happening. In order to do that, what it means is that I'm going to have to spend a lot of time in order to get that specific behavior to come about in my software. So what was one instruction in the original machine may end up being lots of instructions on my new machine. But fortunately for me, machines now are a lot faster than the old ones. But I have to be really careful as far as the timing of devices goes. So I think I have an example here of devices in communication. Let's see. There we go. What you're looking at is a screenshot of my emulator with the console open. Let's see, I think I actually have this saved on this computer. As the emulator is running, my CPU is constantly fetching, decoding, and executing instructions. But the way it actually represents these things inside the computer is kind of, well, it's a nuisance to me. It's kind of interesting to you. If I look at the console, what I've got is information representing the different graphics. If you look up here at the top right, you can see, it's kind of blurry, I don't know if you can see. But you can see all the letters and graphics that are being used here. What essentially has happened is that the bits are being converted to numbers, and the numbers are going out to a big palette of colors and looking up the colors that are being used. The shapes and the colors come together and are mapped out on the screen as output. So now my output device, I understand how the numbers work, but these things are made real by the emulator. If you notice that the constant change going on inside video memory indicates that bytes are going back and forth between the processor and the display device. We'll come back to this in a second. So, needless to say, if I don't emulate accurately, I get something like this happening. These are the same thing that we're looking at here. The one on the left has a glitch in my display emulation. I actually did one bit backwards inside. One bit, the smallest possible error you could make, and I made it. The thing on the left that we're looking at here, I don't know if you can see, this guy has numbers instead of shoulders, and he looks like he's missing part of his head here. A glitch in the display emulation meant that one number wasn't getting processed, which meant that when it looked for graphics, it was looking in the wrong place, and so it was pulling out things from its display font and putting them in instead of graphics that were meant to show us all a picture. Here's another sort of inaccuracy. I don't know if you can even tell what that one is. This game uses many, really many features that I never finished in my emulator. So it's very possible that one small mistake has serious consequences. We do sound emulation in kind of an interesting way. inside the hardware we had a number of square wave generators. Now anybody in here taken physics before? A few people, right? A square wave is one of the simplest things you can think of. It's either all up or all down, and it goes exactly at the same time from one to the other. That's how sound was made. And so all I was doing was reproducing those things. Now, my emulator might be going faster, it might be going slower than the original computer intended. How do I keep my audio from falling out of sync? I have to know when to use the actual behavior of the machine sometimes and when to appeal to, oh, the real computer has a clock and it can tell you how much time has gone by sometimes. Now, the project, now that it's sort of nearing its release, has a number of benefits over the original hardware. As I mentioned before, this will never break if I sit on it. Well, I guess I could sit on my laptop, but that's a different story, right? This software can be run on any one of a number of devices. It can be run on a desktop computer, or I can load it up on a Raspberry Pi and play it on a TV. I could load it on my phone. I don't recommend, by the way, playing phone games during class either. But I can make the display more realistic than real, because the original system had limitations that I don't have to impose. For example, the original system could only display 8 moving sprite character graphics on a line before it said, I've had enough, I don't have enough time to draw 9. I don't have to impose that same restriction. I can either make the display really realistic and imitate what it would look like on a TV, or I can make it more accurate than the real thing and have sharp pixel edges. Basically, the world is my oyster, right? Because once this thing is a program, I can write it as I see fit. So, the industry knows that these things are out there. As a matter of fact, I want to say 4, but it's really 3. All of the 3 big video game manufacturers produce their own emulators now. They are doing this in order to continue selling you the White Album over and over, right? They can sell you Tetris for $2 if you want it on your phone, or $10 if you want it on your computer, or $20 if you want it on something else. Emulation is being used as an alternative to test new software on real devices. Those of you who are in my 353 class know that. The Android development environment that we're using in there toward the end of the semester doesn't even require you to have a phone to be able to write a piece of software, because you can write your program, run it on your computer as though it were on a phone, and test it out that way. So emulation has a number of uses. As to the original status of the project BlameGear, as of this presentation, 52 of the games I tested work perfectly. They work exactly as the original system intended. 5 of them have various kinds of glitches, and 8 of them are just completely broken. They don't work at all. So it's still sort of an ongoing project, but these are the things that keep up a young computer scientist all night and make his wife very angry at him. For any future updates on this project, you can visit the website up here, which I'm not going to pronounce for you, but it was unique on Google. If there are any questions you have about emulators, now I'd like to take the opportunity to hear them out. Thank you.